Unit 3 Classification of Elements and Periodicity in Properties. We need to classify elements. The elements are the basic units of all types of matter. At present, 114 elements are known. Of them, the recently discovered elements are man-made. Efforts to synthesize new elements are continuing. With such a large number of elements, it's very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists searched for a systematic way to organize their knowledge by classifying the elements. Not only that, it would rationalize known chemical facts about elements, but even predict new ones for undertaking further study. Genesis of periodic classification. The German chemist Johann Dobereiner in early 1800s was the first to consider the idea of trends among properties of elements. By 1829, he noted a similarity among the physical and chemical properties of several groups of 3 elements, triads. In each case, he noticed that the middle element of each of the triads had an atomic weight about halfway between the atomic weights of the other 2. Also, the properties of the middle element were in between those of the other 2 members. Dobereiner's relationship, referred to as the law of triads, seemed to work only for a few elements. The English chemist John Alexander Newlands in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every 8th element had properties similar to the first element. Newland's law of octaves seemed to be true only for elements up to calcium. The periodic law as we know it today owes its development to the Russian chemist Dmitry Mendeleev 1834 to 1907 and the German chemist Lothar Meyer 1830 to 1895. Working independently, both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. While Dobereiner initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. It states as follows: the properties of the elements are a periodic function of their atomic weights. Mendeleev arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical column or group. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compounds formed by the elements. Modern periodic law and the present form of the periodic table. In 1913, the English physicist Henry Moseley observed regularities in the characteristic of X-ray spectra of the elements. A plot of square root of V, where V is the frequency of X-rays emitted, against atomic number Z gave a straight line and not the plot of square root of V versus atomic mass. He thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was therefore accordingly modified. This is known as the modern periodic law and can be stated as: the physical and chemical properties of the elements are periodic functions of their atomic numbers. the atomic number is equal to the nuclear charge, that is, number of protons, or the number of electrons in a neutral atom. The periodic law is essentially the consequence of the periodic variation in electronic configurations, which indeed determine the physical and chemical properties of elements and their compounds. A modern version, the so-called long form of the periodic table of the elements, is the most convenient and widely used. The horizontal rows, which Mendeleev called series, are called periods, and the vertical columns groups. Elements having similar outer electronic configurations in their atoms are arranged in vertical columns, referred to as groups or families. According to the recommendation of International Union of Pure and Applied Chemistry, IUPAC, the groups are numbered from 1 to 18, replacing the older notation of groups 1A, etc., 7A, 8, 1B, etc., 7B, and 0. There are altogether 7 periods. The period number corresponds to the highest principal quantum number, n, of the elements in the period. The first period contains 2 elements. The subsequent period contains 8, 8, 18, 18 and 32 elements respectively. The 7th period is incomplete and, like the 6th period, would have a theoretical maximum on the basis of quantum numbers of 32 elements. In this form of the periodic table, 14 elements of both 6th and 7th periods, lanthanoids and actinoids respectively, are placed in separate panels at the bottom. Nomenclature of elements with atomic numbers greater than 100. The naming of the new elements has been traditionally the privilege of the discoverer or discoverers, and the suggested name was ratified by the IUPAC. The IUPAC has made recommendation that until a new element's discovery is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element, using the numerical roots for 0 and numbers 1 to 9. The roots are put together in order of digits which make up the atomic number, and IUM is added to the end. Thus, the new element first gets a temporary name with symbol consisting of 3 letters. Later, permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country or state of the country in which the element was discovered, or pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Electronic configurations of elements and the periodic table. An electron in an atom is characterized by a set of 4 quantum numbers, and the principal quantum number n defines the main energy level known as shell. The distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. Electronic configurations in periods. The period indicates the value of n for the outermost or valence shell. In other words, successive period in the periodic table is associated with the filling of the next higher principal energy level. N is equal to 1, n is equal to 2, etc. The number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period, n is equal to 1, starts with the filling of the lowest level 1s and therefore has 2 elements, hydrogen 1s raised to 1 and helium 1s raised to 2. when the first shell K is completed. The second period n is equal to 2 starts with lithium and the third electron enters the 2s orbital. The next element, beryllium, has 4 electrons and has the electronic configuration 1s raised to 2, 2s raised to 2. Starting from the next element, boron, the 2p orbitals are filled with electrons when the L shell is completed at neon, 2s raised to 2, 2p raised to 6. Thus, there are 8 elements in the second period. The third period, n is equal to 3, begins at sodium and the added electron enters a 3s orbital. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. The fourth period, n is equal to 4, starts at potassium and the added electrons fill up the 4s orbital. Before the 4p orbital is filled, filling up of 3d orbitals becomes energetically favorable and we come across the so-called 3d transition series of elements. This starts from scandium, Z is equal to 21, which has the electronic configuration 3d raised to 1, 4s raised to 2. The 3d orbitals are filled at zinc, Z is equal to 30, with electronic configuration 3d raised to 10, 4s raised to 2. The fourth period ends at krypton with the filling up of the 4p orbitals. Altogether, we have 18 elements in this fourth period. The fifth period, n is equal to 5, beginning with rubidium, is similar to the fourth period and contains the 4d transition series starting at yttrium, Z is equal to 39. This period ends at xenon with the filling up of the 5p orbitals. The sixth period, n is equal to 6, contains 32 elements and successive electrons enter 6s, 4f, 5d and 6p orbitals in the order. Filling up of the 4f orbitals begin with cerium, Z is equal to 58 and ends at lutetium, Z is equal to 71, to give the 4f inner transition series, which is called the lanthanoid series. The seventh period, n is equal to 7, is similar to the sixth period with the successive filling up of the 7s, 5f, 6d and 7p orbitals and includes most of the man-made radioactive elements. This period will end at the element with atomic number 118, which would belong to the noble gas family. Filling up of the 5f orbitals after actinium, Z is equal to 89, gives the 5f inner transition series known as the actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Group-wise electronic configurations. Elements in the same vertical column or group have similar valence shell electronic configurations, the same number of electrons in the outer orbitals and similar properties. For example, the group 1 elements alkali metals all have ns raised to 1 valence shell electronic configuration. Thus it can be seen that the properties of an element have periodic dependence upon its atomic number and not on relative atomic mass. Electronic configurations and types of elements S, P, D, F blocks. The elements in a vertical column of the periodic table constitute a group or family and exhibit similar chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in their outermost orbitals. We can classify the elements into 4 blocks, namely S block, P block, D block, and F block, depending on the type of atomic orbitals that are being filled with electrons. We notice 2 exceptions in this categorization. Strictly, helium belongs to the S block, but its positioning in the P block along with other group 18 elements is justified because it has a completely filled valence shell 1s2 and as a result exhibits properties characteristic of other noble gases. The other exception is hydrogen. It has only one s electron and hence can be placed in group 1 alkali metals. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to a group 17 halogen family elements. Because it's a special case, we shall place hydrogen separately at the top of the periodic table, the S block elements. The elements of group 1 alkali metals and group 2 alkaline earth metals, which have Ns1 and Ns2 outermost electronic configuration, belong to the S block elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electrons readily to form 1+ ion in the case of alkali metals or 2+ ion in the case of alkaline earth metals. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. The P block elements. The P block elements comprise those belonging to group 13 to 18, and these together with the S block elements are called the representative elements or main group elements. The outermost electronic configuration varies from Ns2 Np1 to Ns2 Np6 in each period. At the end of each period is a noble gas element with a closed valence shell Ns2 Np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition or removal of electrons. The noble gases thus exhibit very low chemical reactivity. Preceding the noble gas family are 2 chemically important groups of nonmetals. They are the halogens, group 17, and the chalcogens, group 16. These 2 groups of elements have highly negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. The D block elements, transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbitals by electrons and are therefore referred to as d block elements. These elements have the general outer electronic configuration n-1 d raised to 1 to 10 ns raised to 0 to 2, except for Pd, where its electronic configuration is 4d raised to 10, 5s raised to 0. They are all metals. They mostly form colored ions, exhibit variable valence, oxidation states, paramagnetism, and oftenly used as catalyst. However, zinc, cadmium, and mercury, which have the electronic configuration n-1 d raised to 10 ns raised to 2, do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metals of S-block elements and the less active elements of groups 13 and 14, and thus take their familiar name transition elements. The F-block elements, inner transition elements. The two rows of elements at the bottom of the periodic table, called the lanthanoids, Ce, Z is equal to 58, to Lu, Z is equal to 71, and actinoids, Th, Z is equal to 90, to Lr, Z is equal to 103, are characterized by the outer electronic configuration n-2 F raised to 1 to 14, n-1 d raised to 0 to 1 n s raised to 2. The last electron added to each element is filled in f orbital. These two series of elements are hence called the inner transition elements, F-block elements. They are all metals. Within each series, the properties of the elements are quite similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoid elements. Actinoid elements are radioactive. Many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. Metals, nonmetals, and metalloids. The elements can be divided into metals and nonmetals. Metals comprise more than 78% of all known elements and appear on the left side of the periodic table. Metals are usually solids at room temperature. Mercury is an exception. Gallium and cesium also have very low melting points, 303 K and 302 K respectively. Metals usually have high melting and boiling points. They are good conductors of heat and electricity. They are malleable, can be flattened into thin sheets by hammering, and ductile, can be drawn into wires. In contrast, nonmetals are located on the top right-hand side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to non-metallic on the right. Nonmetals are usually solids or gases at room temperature with low melting and boiling points. Boron and carbon are exceptions. They are poor conductors of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. The non-metallic character increases as one goes from left to right across the periodic table. The change from metallic to non-metallic character is not abrupt. The elements, example, silicon, germanium, arsenic, antimony, and tellurium, running diagonally across the periodic table, show properties that are characteristic of both metals and nonmetals. These elements are called semi-metals or metalloids. Periodic trends in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 nonmetals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of nonmetals, say halogens, reactivity decreases down the group. Trends in physical properties. There are numerous physical properties of elements such as melting and boiling points, heats of fusion and vaporization, energy of atomization, etc., which show periodic variations. Atomic radius. One practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value, the covalent radius of that element can be calculated. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. Atomic radius referred to both covalent or metallic radius depending on whether the element is a nonmetal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic size generally decreases across a period. It is because within the period, the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number. For alkali metals and halogens, as we descend the groups, the principal quantum number n increases and the valence electrons are further from the nucleus. This happens because the inner energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. The atomic radii of noble gases are not considered here. Being monoatomic, their non-bonded radii values are very large. In fact, radii of noble gases should be compared not with the covalent radii, but with van der Waals radii of other elements. Ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. In general, the ionic radii of elements exhibit the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. Some atoms and ions which contain the same number of electrons, we call them isoelectronic species. Two or more species with the same number of atoms, same number of valence electrons, and same structure, regardless of the nature of elements involved. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. Ionization enthalpy. A quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom X in its ground state. The first ionization enthalpy for an element X is the enthalpy change delta I capital H for the reaction depicted in equation Xg gives X plus G plus E minus. The ionization enthalpy is expressed in units of kJ per mole. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in equation 3.2. X plus G gives X2 plus G plus E minus. Equation 3.2. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it's more difficult to remove an electron from a positively charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second, and so on. The term ionization enthalpy, if not qualified, is taken as the first ionization enthalpy. You will find maxima at the noble gases which have closed electron shells and very stable electron configurations. On the other hand, minima occur at the alkali metals, and their low ionization enthalpies can be correlated with their high reactivity. In addition, the first ionization enthalpy generally increases as we go across a period and decreases as we descend in a period. The ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors. One, the attraction of electrons towards the nucleus, and two, the repulsion of electrons from each other. The effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening core electrons. In general, shielding is effective when the orbitals in the inner shells are completely filled. This situation occurs in the case of alkali metals, which have single outermost NS electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not change very much to compensate for the increased attraction of the electron to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increases across a period. As we go down a group, the outermost electron being increasingly farther from the nucleus, there is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy down a group. When we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. Therefore, it is easier to remove the 2p electron from boron compared to the removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, 3 2p electrons reside in different atomic orbitals, Hund's rule, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the 4th 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. Electron gain enthalpy. When an electron is added to a neutral gaseous atom X to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy delta EG(H). Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form anion, as represented by equation Xg plus E minus gives X minus G. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, Energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements, the halogens, have very high negative electron gain enthalpies because they can attain stable noble gas electronic configurations by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gases. The variation in electron gain enthalpies of elements is less systematic than for ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom, since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group because the size of the atom increases and the added electron would be farther from the nucleus. This is generally the case. However, electron gain enthalpy of O or F is less negative than that of the succeeding element. This is because when an electron is added to O or F, the added electron goes to the smaller n is equal to 2 quantum level and suffers significant repulsion from the other electrons present in this level. For the n is equal to 3 quantum level S or Cl, the added electron occupies a larger region of space and the electron-electron repulsion is much less. Electronegativity, a qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself, is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, a number of numerical scales of electronegativity of elements, namely Pauling scale, Mulligan-Jaffe scale, Allred-Roschow scale, have been developed. The electronegativity of any given element is not constant. It varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decrease down a group, say from fluorine to astatine in the periodic table. The attraction between the outer or valence electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases. On the same account, electronegativity values decrease with the increase in atomic radii down a group. The trend is similar to that of ionization enthalpy. Non-metallic elements have strong tendency to gain electrons. Therefore, electronegativity is directly related to that non-metallic properties of elements. It can be further extended to say that the electronegativity is inversely related to the metallic properties of elements. Thus, the increase in electronegativities across a period is accompanied by an increase in non-metallic properties or decrease in metallic properties of elements. Similarly, the decrease in electronegativity down a group is accompanied by a decrease in non-metallic properties or increase in metallic properties of elements. Periodic trends in chemical properties. Periodicity of valence or oxidation states. The valence is one of the most characteristic property of the elements and can be understood in terms of their electronic configurations. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and or equal to 8 minus the number of outermost electrons as shown below. The term oxidation state is frequently used for valence. The oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. Anomalous properties of second period elements. The first element of each of the groups 1. Lithium and 2. Beryllium and groups 13 to 17 boron to fluorine differs in many respects from the other members of their respective group. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, form compounds with pronounced covalent character. The other members of these groups predominantly form ionic compounds. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group, that is, magnesium and aluminum respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior for the first member of a group of elements in the S and P blocks compared to that of the subsequent members in the same group? The anomalous behavior is attributed to their small size, large charge to radius ratio, and high electronegativity of the elements. In addition, the first member of group has only 4 valence orbitals 2s and 2p available for bonding, whereas the second member of the groups have 9 valence orbitals 3s, 3p, 3d. As a consequence of this, the maximum covalency of the first member of each group is 4. Example, boron can only form BF4-, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. Example, aluminum AlF6 3- forms. Furthermore, the first member of p block elements displays greater ability to form p-pi to p-pi multiple bonds to itself. Example, CC, C triple bond C, N double bond N, N triple bond N, and to other second period elements. Example, C double bond O, C double bond N, C triple bond N, N double bond O, compared to subsequent members of the same group. Periodic trends and chemical reactivity. All chemical and physical properties are a manifestation of the electronic configuration of elements. The atomic and ionic radii generally decrease in a period from left to right. As a consequence, the ionization enthalpies generally increase with some exceptions, and electron gain enthalpies become more negative across a period. The ionization enthalpy of the extreme left element in a period is the least, and the electron gain enthalpy of the element on the extreme right is the highest, negative. Note, noble gases having completely filled shells have rather positive electron gain enthalpy values. This results in high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left among alkali metals is exhibited by the loss of an electron leading to the formation of a cation, and at the extreme right among the halogens shown by the gain of an electron forming anion. This property can be related with the reducing and oxidizing behavior of the elements. However, here it can be directly related to the metallic and non-metallic character of elements. Thus, the metallic character of an element, which is highest at the extremely left, decreases and the non-metallic character increases while moving from left to right across the table. The chemical reactivity of an element can be best shown by its reactions with oxygen and halogens. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is the most basic, example Na2O, whereas that formed by the element on extreme right is the most acidic, example Cl2O7. Oxides of elements in the center are amphoteric, example Al2O3, As2O3, or neutral, example CO, NO, N2O. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas neutral oxides have no acidic or basic properties. Among transition metals, 3D series, the changes in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals 4F series. The ionization enthalpies are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease, with exception in some third period elements in electron gain enthalpies in the case of main group elements. Thus, the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property. In the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. Summary. In this unit, you have studied the development of the periodic law and the periodic table. Mendeley's periodic table was based on atomic masses. Modern periodic table arranges the element in the order of their atomic numbers in 7 horizontal rows, periods, and 18 vertical columns, groups, or families. Atomic numbers in a period are consecutive, whereas in a group they increase in a pattern. Elements of the same group have similar valence shell electronic configuration and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right and therefore have different valencies. 4 types of elements can be recognized in the periodic table on the basis of their electronic configurations. These are S block, P block, D block, and F block elements. Hydrogen, with 1 electron in the 1s orbital, occupies a unique position in the periodic table. Metals comprise more than 78% of the known elements. Non-metals, which are located at the top of the periodic table, are less than 20 in number. Elements which lie at the borderline between metals and non-metals, example Si, Ge, As, are called metalloids or semi-metals. Metallic character increases with increasing atomic number in a group, whereas decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electronegativity, and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increase across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies in general become more negative across a period and less negative down a group. There is some periodicity in valence, for example, among representative elements. The valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity is highest at the two extremes of a period and is lowest at the center. The reactivity on the left extreme of a period is because of the ease of electron loss or low ionization enthalpy. Highly reactive elements do not occur in nature in free state. They usually occur in the combined form. Oxides formed of the elements on the left are basic, and of the elements on the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral.